amplifier. This is my name is Samson Shwesh. This is the table of contents, the introduction, and the OB amp, and the inverting amplifier, non-inverting amplifier. This is the OP amp. You see here diff amp, Morse diff chain, and a class B push pole emitter follower. The input stage is the diff amp, followed by Morse diff chain and a class B push pole emitter follower, because the diff amp is the first stage. It determines the input characteristics of the OP amp. And this is the symbol, as you see here, non-inverting input and inverting input. It has single output. It's a schematic symbol of an OP amp. It has non-inverting and an inverting inputs and a single ended output. The inverting amplifier is the most basic OP amp circuit. It uses negative feedback to stabilize the overall voltage gain. The reason we need to stabilize the overall voltage gain is because the gain voltage overloop is too high and unstable to be of any use without some of form of feedback. Inverting negative feedback. The input voltage is amplified by the open loop voltage gain to produce an inverted output voltage. The output voltage is feedback to the input through feedback resistor RF. This results in negative feedback because the output is 180 degrees out of the phase with the input. In other words, any change in V2 produced by the input voltage are offset by the output voltage. I see here is a virtual ground. This type of ground is widely used uh, shortcut for analyzing an inverting amplifier. With a virtual ground the analysis of inverting amplifier and related circuits becomes incredibly easy. The concept of a virtual ground is based on an ideal OP amp. When OP amp is ideal, it has infinity open loop with the voltage and gain and infinity output resistance. The voltage gain is the voltage when there is a feedback path between the output and the input. Because of the negative feedback, the closed loop voltage gain is always smaller than the open loop voltage gain. As you see here, this is the rules or formulas to use it. Vn equals uh, In multiply R1 and V out equals In multiply Rf. And here is the voltage gain in the closed loop is equals V out over Vn, which equals minus Rf over Rn. The input impedance. This is one of the advantages of an inverting amplifier. It is easy to set up a desired input impedance. Here is why. Since the right end of Rn is virtually grounded, the closed loop input impedance is Zn closed loop equal to R1. The bandwidth, the open loop bandwidth or cutoff frequency of an op amp is very low because of the internal compensating capacitor. When negative feedback is used, the overall bandwidth increases. The bias and offset. Negative feedback reduces the input or error caused by input bias current, input offset current, and input offset voltage. Here's some equations to solve. What type of the amplifier is it? Find the output voltage if the input voltage is 5 millivolts. For the first question, as you see here, guys, the source um, is connected to the R1 to the minus side of the AC. That means this is an inverting amplifier. For the second question, find the output voltage if the input voltage is 5 millivolt. You can use this formula to find the the output voltage. Next question: What type? What is the type of amplifier? Find the voltage gain of the circuit. The same, since the source connected to the minus side of the AC or the amplifier, the OP amp. It is an inverting amplifier. For this question, you can use this formula to find, as you see here, the gain equals minus RF over Rn equal to minus 100K over 10K equals minus 10 millivolts. The non-inverting amplifier is another basic op-amp circuit. It uses negative feedback to stabilize the overall voltage gain. With this type of amplifier, the negative feedback also increases the input impedance and decrease the output impedance. An input voltage Vn drives the non-inverting input. This input voltage is amplified to reduce the in-phase output voltage. Part of output voltage is feedback to the input through a voltage divider. The voltage across R1 is the feedback voltage applied to the inverting input. This feedback voltage is almost equal to the input voltage because of the high open loop voltage gain. The difference between V1 and V2 is very small. Since the feedback voltage offsets the input voltage, we have negative feedback. There is also a virtual short between V1 and V2. The voltage gain, since no current can flow through a virtual short, the same I1 current must flow through RF, which means that the output voltage is given by V out, because I1 multiply RF plus R1, and to get the voltage gain, we can use either this rule or this rule, RF plus R1 over R1, or RF over R1 plus 1 is the equation. Uh, Find the closed loop gain of the amplifier. As is here in the first question, we can use the rule for a non-inverting amplifier, which is equals to A closed loop RF over R1 plus 1, which equals here RF is 100K over 5K, which is R1 equals 5. We see here why this is a non-inverting amplifier, because the Vn is connected to the right to the plus side of the op amp. This is how the non-inverting circuit looks like. Find the V out of the amplifier if 1 millivolt DC signal is applied to the input. We can multiply them immediately because we have the gain. So V out equals 5 multiply 1 millivolt equals 5 millivolts. This is the for V out. That's it. Thank you for listening. Masalam. Goodbye. This is the end of the project. Thank you for listening. Goodbye. Masalam.